So kinetics is how fast, okay? And we will determine how fast a reaction occurs by looking at how fast the reactant decays. For this particular equation, A goes to B. We will determine how fast this reaction occurs by measuring the decay of A. Okay? And that is given by a rate law. Rate means how fast. Okay? It is some concentration over time. Brackets means moles over liter. Brackets means molarity. Okay? So the important key point of this chapter, which we will discuss in subsequent pages, is this idea of a rate law. How fast a reaction occurs is based upon this rate constant lowercase k. We'll call it the rate constant. How fast this A to B reaction occurs is based upon the concentration, the starting material of A, or any reactant. It could be A and B. So the concentration, initial concentration of reactant. And then this X here is kind of tricky, okay? But this X stands for order of decay. It's an exponent. It's raised to the power of X. Okay? And you have to find X in the problem. Okay? The order of the decay for reactant. For here it's reactant A. For this one would be the order of decay for reactant A and reactant B. So this is an exponent. It's raised to the power. Okay? So I'll highlight this here. So this X in this class, this X will take on three values. Okay, this exponent X can be 0. That means A concentration decays with 0 order kinetics. Okay, so this has its own equation for half-life. Okay, decay. A is going down. Product B is going up. This exponent can be raised to the power of 1. That means A, concentration of A, decays with first order kinetics. So first order half-life, first order equations. This exponent can be 2. And if this exponent is 2, that means this concentration of A is going to decay by a second order kinetics. That has its own half-life. First order has its own half-life. 0 order has its own half-life. We do not have to memorize these equations. You can, I'll give them to you. But second order kinetics. So that is one of the main points here. Let me give you some things about. So let's look at this one here. What would be the rate law for this reaction? Reactants A plus B goes to C plus D. It's going to be equal to rate times its own rate constant times the concentration of A raised to its order of decay, 0, 1, 2, or 3. Times the concentration of B raised to its order of decay, 1, 2, or 0, 1, 2. Okay, 0, 1, or 2. Right, so we got to find X, we got to find Y, and we got to find rate constant K. Okay, for this, reaction. You substitute real chemicals here. Okay, we got to find X and we got to find K for this reaction. You substitute real chemicals. Okay, so that's what we're going to be doing here. It's called a rate law. All right, let me give you some terms about K here. Okay, this K is lowercase and it means rate constant, I'm sorry. Okay. And it's quoted at a specific temperature. Okay, some qualities of this rate constant. So, okay, it's quoted at a specific temperature. If you change the temperature, the reaction will either increase or decrease in its speed, and that will change the rate constant. Okay, increase the temperature, usually you increase the rate constant. Reaction has a faster rate. Decrease the temperature, usually lower the speed of the reaction, it will decrease the rate, how fast it will occur. So this rate constant K is quoted at a specific temperature. Okay, there is also vapor pressure from last chapter, also quoted at a specific temperature. Vapor pressure, if you remember that. The units are going to change from problem to problem. Okay, units will change from one homework problem, or from one problem to problem. From one, I guess, reaction to another reaction. Okay, so the units vary, is what I'm trying to say. Okay, so when we do rate law problems, which we will do next week together, okay, we'll find out that our units are going to, they're not consistent, okay? From one homework problem to homework problem, from one example problem to the example problem. So this K, you got to figure out the units, which is kind of difficult, okay? Okay, and finally, this is a rate constant K quoted at a specific temperature. The units they change. And then finally, this is something I want you to know. Do not confuse with capital K, which is equilibrium constant. It's totally different. Okay, totally different situation. Okay.
Was that in Gen Chem 1 for equilibrium constant?
No, this will something we'll study in chapter 14. Okay, equilibrium. Maybe you got a little bit, but chapter 14. Okay, deep dive into that. But right now we will go into a deep dive here in chapter 13. How fast? Kinetics. Okay, kinetics. How fast? All right. Any questions here? So that's the main topic for this chapter, plus a couple other things as well. All right, before we go into rate law, let's... Uh-oh. Okay. Oh, well, that's how it is going to be. Okay, before we go into rate law, let me introduce something here called rate expression. Okay, it's very different than rate law. We'll just do one problem on it before we go into the rate law. Okay, so just want to give you this very basic. Okay, a rate expression. So you see here, 2 molecules of H2O2 are decaying to 2 molecules of water and 1 molecule of oxygen. So if we want to do a rate expression, this is going to decay at -1/2 change in concentration. Remember, brackets mean concentration over time. As this decreases by, why is it the minus? Because it's decreasing. Okay, why the minus? It's decreasing. This is going to equal the formation of H2O2, 1/2 times the change in concentration of H2O times delta T. Okay, why is it positive? Because it's a product, and that's going up. And that's going to equal the change in concentration of O2 over time. Okay, so this is the rate expression. It's not the rate law, it's a rate expression. You take the 1/2 and you take that 1/2, you invert it. You take the 2 here, you invert it. This is 1, you invert 1, which is 1. So this is called the rate expression. So this is going to decay by negative 1/2 as this increases by 1/2 and this increases by a factor of 1. Okay, that is the expression. Okay, this is not rate law, which is something else. So you're going to take the reciprocal, and this is the change in concentration over time. Okay, so let's do a rate expression for a problem on page 3. Okay, I'll just talk about it, but I'm not going to focus too much on it. Okay, we will focus on the rate law. Let's do a rate expression for this one here on page 3. Okay, when you do a rate expression, we take the inverse of the coefficients. So rate expression here, we'll do this, and then we'll actually go to the rate law. Okay. All right, so we have CH4. This is a reactant. Do you agree? So will it increase or decrease over time? Over time. Okay, over time this will decrease. By how much? Okay, is this balanced? 1, 4, 4, 4. Okay, since this is balanced, this coefficient is 1, so this will decrease by a factor by the change in concentration of CH4 over some increment of time. Okay, this rate of decay will equal to the rate of decay of O2 by what factor? 1/2 the change in concentration of O2 over some increment of time. And this will decrease at this rate, so it's negative. What will increase positively? The products will increase positively at a rate of the change in concentration of CO2 over some increment of time. And how will H2O increase? Positive or negative? It's a product, so it's going to be 1/2 change of H2O over delta T over some increment of time. Okay, so that is the rate expression. Okay, it's negative because these are products. They're going to go down over time. This is positive. They're going to go up over time. Okay, we will take the inverse of the coefficient. The rate of decrease of this should equal the rate of decrease of O2 by 1/2 because we have 2 moles, should equal the rate of increase of CO2, should equal this rate of increase of H2O by 1/2 because we actually have 2 moles here. Okay, so that's how the expression works. All right, let's do one with some real numbers here. Okay, suppose H2 is being formed at a rate of 0.078 molarity over seconds. Okay, notice this is some concentration over time. How fast? Not miles per hour. Okay, concentration over time. At what rate is P4 being formed? At what rate is pH3 being reacted? Okay, so let's first write the rate expression here. It's formed at this rate. Okay, let's first write the rate expression. So this is balanced. So this is going to decrease minus, because it's a reactant, 1/4 the change in concentration of pH 3 over some increment of time. Okay, over that same window of time, this will increase in the rate expression. P4 is a product, so it's going to increase by some change in concentration over that same increment of time. The H2 is being formed at a rate of 6, so this is going to equal 1/6 the change in concentration of H2, okay, over that same increment of time. So you have a window of time. This is going to decrease by 1/4. This is a product that will increase by a factor of 1, because you're only making 1, and this will increase by a factor of 1/6 because you're making 6. Okay, so that's the rate expression. So it's saying H2 is being formed at a rate of 0.078. H2 is being formed at a rate of 0.078. So if it's being formed at the rate of 0.078, we'll take that 1/6. Okay. Put that here. Actually, let's just do this. We're only concerned with this and this, right? So we're not concerned with that. So this, minus 1/4 the rate of pH 3 over delta T. Okay. Okay, this is going to equal to 0.078. Okay. So this delta pH 3 over time will decrease at a rate of 0.078 molarity per seconds. Okay, times 4. This P4, okay, will increase at a rate of 0.078 molarity per seconds. So this is 0.078 times 4. Okay, this is being formed at, this is decaying at a rate of 0.12 molarity over seconds. This is increasing at 0.078 molarity over seconds. And that's the answer. So at what rate is P4 being formed? This is the rate. And at what rate is pH 3 decaying? Okay, it's decaying 0.13, decreasing 0.312 molarity over second. So now let's go into the rate law. So that's that. We will, you'll get exposed to that probably just now. I'm not going to ask you on the quiz, I don't think. And I don't think I'll ask you this on the test, but you may see this in your future, MCAT or whatever big exams you guys are taking later on. For now, let's talk about the rate law. Okay, any questions or comments? Okay, why don't we just do the rate law now in our last 20 minutes of class. Okay, we'll do 2 rate law problems. We'll start this one and then we'll finish it off next week. Okay, so we did a rate expression. You're going to take the inverse change in concentration over some window of time. If it's a reactant, it decreases. If it's a product, it increases. Okay. Okay, something on the exam, something that's common in Chem 2 is this rate law. Okay, remember what the rate law is? Okay, we'll do this problem here. We're going to use this equation, F2 plus 2ClO2 gives you 2FClO2. Okay, here's our equation. Okay, we want to know how fast this reaction is going to occur. How fast this reaction is going to occur is based on a rate law. Okay, not rate expression. Okay, so the rate here is going to be some rate constant K times the reactant F2 and how fast it decays, the order of its decay, times reactant Cl2 times to the power of the order of its decay. All right, so our goal here is to find K, find this exponent A, which is the decay for F2 reactant, and then find exponent B, which is the order of decay for ClO2. Okay, so this reactant can decay with 0 order, first order, or second order kinetics. This reactant B can decay with 0 order, first order, or second order kinetics. Okay, so when you do a rate law, you're going to get a table. Okay, so we'll get a table like this. We got 3 experiments. In this experiment, we got 0.10 molar and 0.010 molar of the other reactant. Second experiment, they quadrupled one of the reactants. And in the third experiment, they doubled the first reactant, keeping the second reactant the same. Okay, so how will we do this problem? Okay, we're going to compare 2 experiments. Okay, so which experiments do you want to compare? You can pick 2 experiments, Asia. Okay, we'll compare 1 and 3. Okay, so we will compare experiments 1 and 3 together. Okay, what are we trying to do? Let me just tell you the main point here. We're trying to find rate constant K and the exponents A and B. Okay, that's what we're trying to do. Okay. So we're going to do this, experiment 1 and experiment 3. Okay, let's just use a fresh sheet of paper here. Comparing experiment 1 to experiment 3. Okay, that is rate 1 over rate 3. Okay, what does the rate law equal? Okay, it's going to equal to some rate constant K times F2 raised to the power of its decay for experiment 1, rate 1, times ClO2 raised to the power of its order of decay, rate 1, experiment 1, divided by K, F2 raised to the power of A, rate 3, experiment 3, times ClO2 raised to the power of B, rate 3, experiment 3. Okay. Comparing experiment 1 with experiment 3. All right, what was rate 1 for experiment 1? Can you tell me, Asia? 10 to the minus 3 molarity over seconds. 1.2 times 10 to the minus 3 molarity over seconds. What is rate 3? 2.4 times 10 to the minus 3 molarity over seconds. Okay, that equals K, which we'll have to find later. What is F2 for experiment 1? 0.10 molar. Okay, raised to what power? Okay, A, we got to find that out. What about ClO2 for experiment 1, rate 1? 0.010. 0.010 raised to the power of B. And then divided by rate 3. So K is we got to find later. What is F2 for experiment 3? Raised to the power of A, its order of decay for F2. And what is ClO2 for experiment 3? .010, right? Raised to the power of B, its order of decay. All right, so the 0.01 molar to the power of B and the 0.010 molar to the power of B cancel. Okay, the rate constant K and K cancel. We'll have to calculate that at the end of this problem. 1.2 times 10 to the minus 3 divided by 2.4 times 10 to the minus 3 is 1/2. Okay, molarity over second cancels. We are left with I'm going to move the brackets outward. Okay, so 0.1 molar cancels. 0.10 divided by 0.20. That whole thing raised to A. The common exponent is A. Okay, 0.10 divided by 0.20 is 1/2. So 1/2 to the power of A. Okay. So what does A equal to here? Does it equal to 0, 1, or 2? Okay, A equals 0. Anything to the power of 0 is what number? 1. A is equal to 1. What's 1/2 to the power of 1? Half. Okay. What's 1/2 to the power of 2? 1/4, 0.25. So what is it? 0, 1, or 2? 1. Yeah, 1. Okay. So F2 is going to decay with first order kinetics. Okay. F2 is going to decay with first order kinetics. And all its associated equations. Actually, all the equations are right here for first order. Okay, this is how F2 will decay. You can use this on the test. Oh, I put it out weird. This is how F2 will decay. This is the half-life for F2 because it's first order. Okay, so we'll go over this next week. So those are the equations for F2, that reactant. All right, let's now try to calculate B. So instead of comparing 1 and 3, what do you think we should compare for? Let's compare 1 and 2. Is that okay? Okay, let's compare experiment 1 and experiment 2. Okay, so rate 1 over rate 2 equals K times the concentration of F2 to the power of A times the concentration of ClO2 to the power of B. That divided by rate 2, the rate law experiment 2, rate 2. Okay, now let's substitute in. Asia, what's rate 1 for experiment 1? Oh, it's right here. 1.2 times 10 to the minus 3 molarity over seconds equals K times F2 is 0.10 molar to the power of A times 0.10 molar to the power of B. Okay, what is rate 2? 4.8 times 10 to the minus 3 molarity over second. Okay, K. What is F2 for rate 2 experiment 2? 0.10. Okay, what is ClO2 for rate 2 experiment 2? What is its concentration? 0.040. This is 0.010. Okay, 0.010. Okay, 0.10 for ClO2 experiment 1. Make sure you copy the right concentration from the table. Right? Okay, make sure you copy the right concentration from the table. All right, 0.10 to the power of A cancels out with 0.10 to the power of A. The K's cancel. 0.1010 divided by 0.040. I'm going to push that bracket outward and make it 0.010 divided by 0.040 to the power of B. What's 1.2 times 10 to the minus 3 divided by 4.8 times 10 to the minus 3? It's 1/4. Okay. So what does B decay by? Okay, what's the exponent B here? Is it 0? It's 1. So just like that, ClO2 is going to decay with first order kinetics. Okay, and just like that other reactant, just like F2, its decay will abide by these equations. Okay, you don't need to know that, but you can use this for the test, and this is its half-life for how fast ClO2 decays. Okay. All right. So our rate law here is rate equals K times F2 raised to the first power times ClO2 raised to the first power. Okay, the overall order of the reaction is 2. Okay, this decays to 1, this decays to 1, so the overall order is, what's 1 plus 1? 2. Okay, so the overall order of the reaction is 2. All right, now our second goal here is to find rate constant K. Okay, many students, this is not the right answer. You have to find the rate constant K. Okay, how will we find the rate constant K? So anybody pick an experiment. Actually, pick 1, 2, or 3. You want to pick 2? Okay. So rate, we can use experiment 2, or 1 or 3. 1, 2, or 3, it doesn't matter. We will use experiment 2. Okay, so rate 2 is equal to K times F2 times ClO2. So what was the rate for rate 2? 4.8 times 10 to the minus 3 molarity over seconds equals K times, what was F2 for experiment 2? 0.10 molar raised to what power? Okay. first. What was ClO2 for experiment 2? 0.040 molar raised to what power? Okay, raised to what power? 1. Okay, 1. Raised to 1. So this is raised to the 1, this is raised to the 1. All right, so now we have to do a little math here. Okay, I'm going to take, what's 0.10 m times 0.040? What is that math? .004 molar squared. Okay, don't forget to multiply the m's. M squared equals 4.8 times 10 to the minus 3 m divided by seconds. Okay, 0.010 m times 0.040 m is 0.004 m squared. Yep. Okay, so we will isolate k. 4.8 times 10 to the minus 3 big M divided by molarity over second divided by 0.004 m squared. Okay, we have to cancel some units, okay, because the units of k are going to vary. Okay, one of these m's will cancel out with one of these m's. One of these m's will cancel out with one of these m's, just giving us molar in the denominator and seconds in the denominator. Okay, so what's 4.8 times 10 to the minus 3 divided by 0.004? 1.2? But what about the units? There's nothing in the numerator, so what are the units? Okay, molar times seconds. Okay, that's the units. Or you can do this. Okay, you can write k as equal to 1.2 m to the minus 1 seconds to the minus 1. You can also do that. Okay, this and this are the same. One of these m's cancels out with one of these m's. This is m squared. M squared. Okay, good catch. Okay, leaving one m left. Okay, leaving one molar left. So what's our final answer that you'll report? Okay, our final answer is rate equals 1.2 divided by m divided by seconds times f2 raised to the first power times ClO2 raised to the first power. Okay, this is the answer you're going to put. Okay, for full points. It's the full correct answer. Okay. Final answer is this. Okay. Okay. Before I let you go, okay, Ashley, for experiment 1, what was the concentration of F2? Experiment 1. Experiment 1. Okay, F2, experiment 1 is 0.10 raised to the first power. Okay, raised to the first power is 0.10 times, what was the concentration of ClO2? 0.01. Okay, times our rate constant 1.2. Okay, what was it? 0.1 times 0.01 times 1.2, and you get 1.2 times 10 to the minus 3 as the rate, and the rate is 1.2 times 10 to the minus 3. So you can double check your answer. Okay, you can do the same thing for experiment 3. Okay. so I will see you all. We'll do one more rate law problem next week. Okay, so you can get practice. This is what you want to report on the exam. Okay, are we going to put the right units on K? Yes. Okay, yes. Okay, are we going to put the right exponents on this reactant and this reactant? Yes. Are we going to frame our answer like this? Yes. Okay. So I'll see you there at 2 o'clock. Okay? Right, you want to wear some gloves and goggles for this one, and PPE, because the cyclohexane and mothballs